This is the third kind that it's harder. What was one of those formulas? And we used double angle formula sometimes. And that was I guess pretty much it. And this one was the case that was a times a sine x plus b times a cosine y, not y, x here. And we can change this whenever a and b are constant. We can change this a times sine x plus b times cosine x into the following form. So anybody remember? We can change it into single sign formula. Anybody remember what those are? There's x in there. Remember this thing? And there's constant k that is determined by this a and b. Anybody remember this? No? Phase shift plus phi. Like that. So these k and phi are absolute constant that is determined by this a and b. And whenever you have this form, a times sine x plus b times cosine x, you can put it back into this addition formula. So you see the addition formula, sine of x plus phi, that's the addition formula. If you expand it, you can imagine it's kind of in this form, right? Applied addition formula here, x is a variable, phi is actual number. Then if you apply it and actually turn those trigonometric values at this phi, then this is going to be the form. And this one is actually requiring doing it backward. That's what this one is. And I hope you see that's this kind right here. Alright? Set equal to 0, and we have to solve for that. Alright, what was the idea? We let this a equals x0, remember? Put that in x0, and what about b? That's going to be y0. Then what do? We go to the xy plane and plot that x0, y0 there, right? And draw a circle like that. And where's the phi? Phi is the angle with that terminal point there, and that's your phi. You have to figure that out. And this r here, radius, is root x squared 0 squared plus y0 squared, right? That came right from the circle equation, not a unit circle equation, it's a circle equation. That x0, y0 is quite random. Draw a circle, you expect some non-unit radius, and there's a phi determined by whatever that point, wherever that is. So given this x0 and y0 we identify, if we can figure out this r, which is going to be the value k in here, and phi, that's going to go in there, and that's how it works. The reason it works like this is x is a cosine, y is a sine, so it fits exactly into the addition formula. Yes? It's just a sample. It could be in the third quadrant, first quadrant, or whatever. Right? When you figure out this phi, approximately, you have to use inverse trigonometry in general. Then inverse trigonometry doesn't always tell you the correct phi value. Remember that part? So you have to figure it out. Phi value. All right? Let's look at this example then. All right. Do you see how you manipulate this one? Algebraically, there are two things when you solve a trigonometry equation. There are two steps you do, right? First one, simple algebraic manipulation, and second one is using this formula as an identity. And we just went over one thing today, which we're going to use. And the other one was a double angle formula that we used last time, right? And what was the other one also used? That was a Pythagorean identity. We also used that one. Okay? The two things we're doing to solve this equation. First one, it seems like we're going to do algebraic manipulation to put it into this form. So do you see that? Sine theta and cosine theta there. And a and b seems like just 1 and -1, things like that. So how about this one in here? If I keep this right-hand side in here, let's just do this. Negative sine theta plus cosine theta plus 1 equals 0. This is what I did. I subtracted sine theta from both sides. Good? There is this 1 here, and that's not really part of this one. Right? So A seems like -1. B seems like +1, right? But there's this one, so you can move that constant to the other side, and then left-hand side will be like this. So here, sine theta plus cosine theta equals what number? -1. I subtracted both sides by 1, so you can end up at there. So we're about to change this one, not algebraically, using this addition formula trick. All right? And you're going to change that, and then it's going to be single trigonometry idea. And then we'll be able to solve it. Okay? So why don't we work on this one like this? We're separating. This is the end of an algebraic manipulation, and then write the second task. Negative sine theta plus cosine theta, we recognize this in that form by addition formula, k times sine x plus phi. I want you to figure that out. So, namely, all you have to figure out is what is that k, what is that phi, right? You have to figure that out. I guess it's lagging a little bit today over the weekend break, so let's just together. All right. Okay. So what's the idea? We take x0. What is x0? -1. And what is y0? +1. Now you see this picture? This picture here? Go ahead and sketch that point. Draw the circle. Figure out what phi is. Figure out what radius is. Let's just do that part together, okay? I feel that you can do that part. And then once you figure out this phi and r, we're going to put it together. And I'm going to explain a little bit more what on earth is going on. I'm going to use the addition formula to explain a little bit more. All right? So here's your exercise. Make it clear. Look at this circle right there. There's all this context. And compute phi, approximate value, and the radius r in that circle over here. You have actual value, -1 and +1. This is a special value, so you will find, some of you will find, hey, that phi is actually, I know the exact value, involving pi, but you can use calculator. All right, how was it? Were you able to plot -1, 1 over there in the second quadrant? And draw the circle, compute the radius to be √2. You see the usual right triangle we put in there to figure out the angle in there? Usually this is the one we put it in there. And that it's 1, 1, √2. So that's 45 degree. So that's why there's a pi over 4 showing up. But the way I introduce it in general, if it is not like this special angle, I will ask you to consider tangent phi. It's very consistent and simple to figure out what the angle that is involved in there. You look at that point, -1, 1, what is tangent phi? Y coordinate divided by x coordinate, right? Just -1. And here, don't just conclude that phi is tangent inverse. That's why I'm writing it different here. I'm just computing tangent inverse of -1, not claiming that this is phi, right? If this angle is in the first quadrant and the fourth quadrant, it is phi. But if not, then you have to do a little bit to get to the other one. All right. The angle they gave you is -0.7853. It's down there in the fourth quadrant, right? Tangent measures the slope of a line. If you extend this line continuously like this, that line, wherever 2 points, the slope is going to be the same. So they actually picked this point, that angle, that one right here. But what you want is the opposite side. So what do we do to get to the opposite side? Just go another 180 degree in radian, go another pi degree, right? So this, if you use tangent to figure out the other angle, it's always consistent. No matter what quadrant, whatever, always just add pi to get to the other side, right? So the answer here is pi plus that angle you just figured out, which is negative 0.7853. All right? So that's roughly what it is. Well, if you do it exactly, that's going to be 3 pi over 4. But I'm going to calculate in decimal. I was not recording all this, but now you see all this thing that you can figure that out. All right, x0, y0 in there. The key thing is that, all right, we have negative sine theta plus cosine theta. That was what we were looking at, right? The magic here, that one we call x0 and y0, cosine theta there, right? And what more complicated thing we did is that x0 is changing to r times, what is it? Cosine phi, right? And there's a sine theta. What is y0? R times sine phi cosine theta. And then, wow, there is this addition formula thing showing up. So r happens to be common. R is pulled out. And what we have there is a sine theta times a cosine phi plus cosine theta plus times a sine phi. Out of nowhere, the simple number, -1 and +1, and then we pulled out this form that you recognize. Sine theta cosine phi plus cosine theta sine phi. What is this? It's the addition formula of which trigonometric function? Sine. You're going backwards. So what is inside here? Sine of what? Right, the theta plus that phi in there. So that was this innocent looking thing, negative sine theta plus cosine theta. Now it became this form where r is root 2, phi is real number 2.3561. More exactly, that's a 3 pi divided by 4. Then it becomes like this. All right? So what? You did make it complicated. See what's the benefit of this one is. The original equation was this negative sine theta plus cosine theta equals -1. Did I copy this right? -1 on the right hand side? Correct? Identically, what happened to the left hand side? Left hand side becomes r times sine theta plus phi equals -1, right? That's what happened to the left hand side. So what kind of algebraic procedure we did here? This was an algebraic procedure. It's an addition formula we use. So going from here to there, by staring at it, you will never understand. It actually behind this much of a calculation in there. All right? Just to speed up the calculation, I would saying that, all right, once you calculate the phi and r, this was the part of a test problem in test 3. So we did that. So let's put aside, let's just go back, just figure out the answer quickly this time. You get that r, go in there. You get that t, go in there. Skip the addition formula. You're allowed to do that in test 4. Yes? All right. So let's save a little bit of time to not doing this one. That's what I'm saying, right? This whole part, you may skip this session. Okay? So we got that number r, phi, that goes right here. Okay, let's do that. What was r? Square root of 2, thank you. Sine times phi theta plus phi, we have that number up there, right? At this point, it's not important to substitute right now, but eventually we will. Because we're going to write down a couple more things with repetitively, so I don't want to turn it into a number right now. Is that okay? But that's -1. All right, only one trigonometry, that's good, right? When you solve trigonometry equation, only one trigonometry function shows up, that's a good part. All right? All right, let's make a little substitution. It's going to look a lot easier. So that looks just like the following. Sine theta, sine of, let's say that was z when we make a substitution. How about that? If I substitute entire thing in there, The z equals the theta plus phi. Theta is unknown. Phi, we know what that is, right? If I substitute it like this, doesn't it look really simple, right? So we're going to make that. Let's not forget this one. We're going to come back to this one. Remember, whenever we make a substitution, you box it and do something to get your attention and come back to figure out the theta value. But now, seems like what we have to do at the moment is that we're going to solve what equation? Root 2 times sine z equals -1. For what variable for now? Z. Solve this equation for z. We're going to come back to this box right here and figure out theta value later. Right now, that's your exercise. Solve this equation for z. Right, was that okay? First, you have to isolate sine z. Then it becomes this simple basic equation. Sine z being -1 over root 2, right? And sine inverse is -0.7853. And there's always one more, right? Pi minus, right? On the unit circle. If you have one over here, there's always another one with the same y coordinates. And that's why there's a two parameterized families of solutions. All right, that's it. That's only z values, right? So we have to go back in here and solve for theta, right? So what is it? What happened with that? Theta is a z, while theta plus phi is the z, right? So what is the theta? Z minus phi, and that phi is, what is that phi value there? Phi value there is really 3 pi over 4 or 2.3561. Just 2.3561. 2.3561 is the value there. All right. So you look at each of this case z and subtract entire thing by this value. Then it's going to be theta value. All right. So let's do that. Here's the theta. What is theta? Z is here, -0.7853, right? And I'm just going to put those two numbers that can be further simplified. So I can put that number -2.3561 here. Is that okay? So that's the z value, one of the z values. And you're supposed to subtract off this 2.3561 from each of the case. So what is the other case? 3.9269 minus 2.3561 plus 2 pi n. Each of the case, we have to subtract off this number. If you further simplify this one, that's going to be your final answer for theta. All right? So I'm just going to pause the video and work this one out. Also, I'm going to write down the exact values since these are all have exact form. So decimal-wise, it was like this. Seems like because we're truncating this number and add and subtract, it caused a little bit of error in there. But if you look at the exact values, this -0.7853 was supposed to be -pi/4. This one was -3 pi over 4. Together is -pi, so it's supposed to be -3.15, something like that. But there's a little error caused by that. And I keep track of these numbers. That was 5 pi over 4. This one was -3 pi over 4. Together is 2 pi over 4. This is pi over 2. So that's, again, it's a little bit of off from there. But these are the exact values. All right? So that's the full answer to that problem right there. Where is it? Oh, there it is. That's the original problem, sine theta. So only thing that you can cut out here, this was just a review part, and that part is a skipping part right there. Other than that, that is what you're going to go through to solve that problem. Lovely. Oh, I can guarantee that. Yes. A little more than that. All right. At least two more. You see two more there? I guess you started it. All right. When I first looked at this equation, there's 3 theta. I don't know the triple angle formula. That was my reaction. But realized, no, you don't relay that triple angle formula. Let me remind you of the problem that used double angle formula. It looked something like this. 3 times the sine 2 theta minus cosine theta equals, let's say, 1/3. It seems like that. This is one of the problem we did. And we used double angle formula to rewrite this one. All right? So let's see. Who remembers double angle formula of sine? When you do the Weber sine problem, try to do it on your own because you're not going to have a formula in the test. All right, what was it again? No? 2, that's right. Sine theta times cosine theta. Thank you, Michael. That was the equation right here. Something like that. I think it was a 0. Other than that, it gets harder. So let me change that to 0. 0 here. Then what did we do? Looking for something common. Cosine theta, sine 2 theta, not common. But after you do this, something is common, right? Cosine theta and cosine theta are common. So what did we do? We factored out. That was b, right? Factored out like this. B is factored out. So we left with 6 times the sine theta minus what number here? 1. Invisible 1 left there. And then this must be 0. And it was split into 2 equations, right? B, that's a cosine theta, must be 0. Or 6 times sine theta minus 1 must be 0. Before there was one equation. Because of the factoring and the right-hand side being 0, we split into 2 equations and handle these 2 equations separately, right? Now, this is our new problem. Maybe that trigger you, I'm going to work this one out, sine triple theta. But it seems like that is the only trigonometry, right? That is the only trigonometry. We did that because here, differently, because there's a sine, there's a cosine. If there was no cosine, probably we can use the same technique we're about to do this example 5 here. All right? Okay. So if I change that 3 theta to z, that becomes a simple trigonometry equation. All right? So let's do that in part A. How about z being what number now? What variable? Z being, substitute something so that this equation is just something actually a lot simpler than usual. Z is going to be 3 theta. Fair enough? That 3 theta inside turned to z, then is going to be 2 times sine z minus 1. That's an equation just like we handle like here. Simple, basic. And we didn't do it here because there was additional trigonometry outside. Does it make the distinction? All right. So we box this one. We're going to return to this one and put a star in there, right? Then our original equation becomes 2 times the sine of what? Z there is minus 1 equals 0, right? I know you can solve this one, so I'm going to make that one exercise. Here's an exercise. Solve this guy. For what variable? Z. Then once you solve for z, and we're going to come back in here and figure out what theta has to be. All right? Okay, that's your exercise. All right, was that okay? Those were the two z values. Those are the exact value. Pi over 6, the 30 degree will give you sine value 1/2. Special value. All right, any question about z? Good. So now we return to theta value, right? How z and theta is related. So since z is 3 theta, what is theta? This is what we want, right? Theta? What is it? 1/3 of z. Correct? 1/3 of z. So you looked at each of the solution, you have to divide it by 1/3, everything. This time, when we added this phi, it only affects this part in here, right? But when we divide, you have to divide this one by 3, also this one by 3. Therefore, it's the first example where your parameterization is adding not 2 pi n, but it's going to be 2 pi over 3 times n is being added. It's very different, more refined family of a solution. All right? So we're not going by multiples of 2 pi, but 1/3 of a multiples of 2 pi. Right? So this type of equation actually occurs a lot in calculus and differential equations in physics, and it actually, you encounter this type of solving this type of equation, where this frequency is integer multiple. This occurs a lot. All right, let's do that here. Therefore, our theta will be simply this everything divided by 3, right? So it's 0.5235 divided by 3 plus this one is usually written like this, 2 pi divided by 3 here times integer n. N is not divided by 3 again. That was one term. That 3 appears only one time in each other term. And the other one is a 2.6179 divided by 3 plus, here's a 2 pi divided by 3. This n is a parameter part just like this. Right? So that was a pi over 6, so this one will be pi over 18 because you divided by 3. So that exact value here is a pi over 18. This one is 5 pi over 6, so it's still 5 pi is there and 18. Those are exact values. But if you do this arithmetic, the final answer in decimal look like this. I'm going to pause the video and do the arithmetic there. So I did the arithmetic. It turns out these are the number when you divide by 3. And what happened to the other numbers here? They stay the same. So 2 pi divided by 3 times n. And the 2 pi divided by 3 times n. All right? So let me go back to the equation. Where is our equation? Equation is there. Yeah. 2 times 3 sine of 3 theta minus 1 equals 0. Entire collection of theta that satisfy this equation must fall into this shape or that shape, where n varies over entire integer, 0, plus minus 1, plus minus 2, and all that. This is a full description of a solution. Make sense? All right. Part B, find solutions in the interval 0 to 2 pi. Remember we did this type of problem between 3 and 40 something. We figured it out, right? By figuring out what kind of n should we consider in this one in here. All right. So let's do this beginning part together and see if we can figure this one out. This is the entire collection of solution, and part B is asking find solutions in where? 0 to 2 pi. Then we're going to take each of the parameterized solution and put this inequality between 0 and 2 pi. Remember that? And solve that inequality in terms of n. N in there. Then we figure out, okay, n should be this and that value. And we plug in 2 or 3 n values there, and you actually get that decimal numbers. So let's start it together. What was the beginning part again? There are 2 types of solutions, so you have to repeat this process 2 times, all right? What do we do? There's this 0.1745, right? Plus 2 pi over 3 times n, is that right? It's supposed to mean between what value and what value? 0 and 2 pi. And you have to solve this inequality for which variable? N. That's right. Here's N. You have to isolate this N, and then you have to figure out N must range from 1 to 2 or something like that. And then you plug in 1 and 2 only here, and that is the solution. You have to repeat the process for the second one. So what is the second step to isolate N? Subtract or multiply? Or divide? We're going to subtract that number. What is that number? 0.1745. Then it's going to be negative 0.1745 over here. By doing that, we kill that negative 0.1745 in the middle. So 2 pi over 3 times n, and 2 pi minus 0.1745. Is this step okay? Everything fine? Then what is the next step then? Add, subtract, multiply, divide. What do we do algebraically? Divide. That's right. But this thing looks weird. If you have to multiply, that's the same procedure, multiply and divide. What would you multiply to kill that 2 pi over 3 in the middle? The reciprocal, right? So we're going to multiply 3 divided by 2 pi to here. If you do that in the middle, you can see the reciprocal cancels. And here is a parenthesis. Make sure you don't lose this parenthesis. And multiply by 3 divided by 2 pi, right? When you do this in a calculator, the 2 pi in the denominator must have a parenthesis around it in the denominator, right? So we're going to figure that out. All right. And so I'm going to pause the video and compute this number in decimals. These are actually exact values. When you do exactly, pi cancels and it gives you nice numbers. But let me just do it this way. So I did that calculation. It turns out these are the numbers, negative 0.0833, and right inside is a 2.19166. And if you're not good at this, I want you to go to the number line and actually locate this number line and make sure you count this correct ends correctly from there. All right? So here's a number line here. Number line. There is negative 0.08, and here is 2.9. What is the immediately to the right integer? The left bound, what is the immediate to the right? What kind of number is there? N. 0, right? 0 is the number. And to the left, there's a negative 1. So 0 is immediately to the right. That's the first one that counts. What about the last one? That comes right before 2.9. N equals 2. So how many values are there? N equals 0, N equals 1, N equals 2. The 3 values, you plug it in there. N equals 0, 1, 2, 0, 1, 2, and those values guarantee that it's going to fall in between 0 and 2 pi. All right? So what are you going to do in the test? I'm not going to do any of this. I'm just going to put n equals 0, n equals 1 until I stay in this part, right? So I told you already I'm not going to like that, right? You have to show this method if it is really wide, right? And complicated, and this method is the mathematical method that you speed up your calculation. All right? So you have to do this method. And we're going to repeat this one on same for the second one again, right? So I'm going to make an exercise I want you to practice. All right. So here's your exercise. All right. So let me finish it here. So n equals 0 and 1 and 2 for the first one, right? I hope you know what I mean by that first one. That was the first line, 0.1745. There's one more here, and you have to determine which n value is proper for the second one, and that's your exercise, right? So solve the second one for n. Maybe 3, maybe 2. We'll see. All right? There are 6 solutions as I plug in 0, 1, 2 and 0, 1, 2 there, and that's the final solution for part B. All right. What do you see? You see any resemblance to what we did before? There was a triple angle. This time was half angle, right? So you're going to use half angle formula? We didn't use triple angle formula. Remember? That was triple angle, 3 theta, but we didn't use triple angle formula. We just substituted it. I hope you see when to use the double angle formula, when not to use double angle formula. So here's what is the thing to do here? First step, not half angle formula. What do we do? Substitute. What is z then? Theta over 2. Then we're going to come back to this one. What happened to the equation? Is it root 3 times tangent of z minus 1 equals 0, right? Do you see that is simply, you can algebraically turn this one into basic equation, right? Where's the tangent z here, right? If you isolate tangent z, what do you see? 1 divided by root 3. This we know how to solve it, right? There's only one solution, remember, for tangent? Oh, it's a good part. So, let me write that down. So what is z? Remember z? 1 over root 3. That's a special angle. Anybody remember what that? You look at the 60, 30 degree. That's where root 3 kick in, right? So is that 30 degree, tangent 30 degree gives you 1 root 3, or 60 degrees? Here's a tall triangle. Where do you see 1 over root 3? From what angle? From 30 here, right? 1 divided by root 3, right? This is 1 here. Root 3, there's a 2. You see that angle must be pi over 6? Here's a pi over 6, right? That's your z0. Then what do we do for tangent? Doesn't have to be 2 line. Tangent is special. It's only one parameter as family, right? What do we add? Tangent case was a pi n, not 2 pi n. Because the slope repeats. If you go across 180 degree across, that's the same slope. 180 degrees, the same slope. That's why. So there's no 2 lines here. That extra solution happened to fall in within that period, pi, that is different from the periods of sine and cosine. Does that make sense? All right, so that's the general solution. That answers part A, right? Part B is the same strategy. We put that one in between 0 and 4 pi, figure out which n value fall in, and so on. So that from here is a repeat, so I'm not going to do that here since we're running out of time. Let me just write that down. All right, here is what we have, right? And solve for n equals, you can work that out, right? So you get the n values, go back and plug in, and that's, I hope this makes sense since we did one example before. All right?